So let me start with some linear algebra background as presented in Rudin. Linear algebra. So in fact, for our purposes, there is no need to talk about abstract vector spaces. So we'll be just dealing with subspaces of Rn. So let us, first thing is a subset X in Rn is a subspace if whenever X and Y belong to X, we have X plus Y belong to X, and if I take any scalar, then Cx belongs to X as well. Right. So the next thing is the concept of a linear combination. If x1, x2, xn are vectors, are elements of Rn, and c1, c2, cn are real numbers, then this c1 x1 plus c1 x1 plus cn xn, this vector is then the vector linear combination of x1 up to, actually I took the same n as this Rn. Of course, they need not be the same, so let me make it xk, and likewise here ck, xk, linear combination of these vectors x1 up to xk. If I have a subset of Rn, then the set span S is defined to be set of all linear combinations of elements of S. Now this, of course, in this definition of the span, this k is not fixed. I can take as many elements from S and then take linear combinations of those elements. Look at the totality of all such linear combinations. That's called the span of S. So if we denote this as Rudin does, if we denote this set by E, then we also say that S spans E. Or E is the span of S. All right. Then the next thing is, let me just quickly see. Yeah, all right. The concept of linear dependence and independence of vectors. So a set of the vectors x1, x2, xk are linearly dependent if, simply put, some linear combination, some non-trivial linear combination of these equal to 0. So if there are C1, Ck in R, not all equal, not all 0. In other words, at least one of them should be non-zero, with C1 x1 plus Ck xk equal to 0. If they are not linearly dependent, then we say that they are linearly independent. Then we say that they are oops, they are linearly independent. So another way of expressing linear independence, i.e. x1, xk are linearly independent if and only if the following happens: whenever any linear combination is 0, of these is 0, that linear combination has to be the trivial linear combination. In other words, we have C1 is 0. Okay. And one immediate thing one can observe is that if so I'll just add it as a remark. If the set of vectors x1, x2, xk, and I'll abbreviate linear independence by just Li, then none of these xi is not equal to 0 for all I. None of these vectors can be 0. And we know why that's true. If one of them is 0, we can take that particular coefficient to be anything we want, for example 1, and the other coefficients to be 0, and I'll get a non-trivial linear combination of these which is equal to 0. Okay. Now we come to the concept of dimension of a vector space. So that was the third point. The fourth one is suppose a subspace X contains a set of R linearly independent vectors, but does not contain any set of R plus 1 linearly independent vectors. Then we say that X has dimension R and write dimension X equal to R. Well, usually dimension is defined in terms of a basis, the number of elements in a basis, but actually this way of putting it is this can be checked to be the same as the basis definition of dimension. So as a again another remark is that if X equal to 0, this is a subspace by going by the definition, and if we well this has if we go by the same definition of dimension that we had just now, there are no linearly independent vectors in this subspace. So then dimension X would be actually equal to 0. The fifth point. Now, this is here we define a basis, a subset x1 xk of X. X is a subspace, is a basis of X if, let's call this subset S, if S is linearly independent and S spans X. In other words, every element of the spanning property, it amounts to saying that every element of X is a linear combination of x1, x2, xk. Now, if you have a basis, then I just said that every element of S is a linear combination of these x1, x2, xk. But the fact that these are linearly independent will imply that the way of writing an element of X as a linear combination of these elements is unique. In other words, note that every X in X can be written as X equal to C1 X1 plus CK XK for unique C1, C2, CK. These constants are unique. So I mean this is an immediate consequence of the linear independence. If you had another linear combination which is also equal to X, you just subtract the 2 and you will get a linear combination of X1, X2, Xk which would be equal to 0. But the linear independence of those vectors would force the coefficients to be 0 and so on. So these, since these are unique, they have you are given a vector, you'll get a bunch of k real numbers, and these are called the coordinates of X. Well, there is also the issue of since the way we have defined dimension doesn't use a basis, there's the issue of whether this k that occurs in the definition of a basis is a fixed number or not. In other words, can we have another basis which has a different for which you have a different number of elements different from k? Of course that it cannot happen, and in fact that will be proved shortly. But at least once we fix a basis, we can talk about coordinates of a vector. The C1, C2, Ck are called the coordinates of X with respect to the basis S. This with respect to is very important. The concept of coordinate makes sense only when you fix a basis. So with respect to S, coordinates of X with respect to S. So here the most basic example is S equal to basis E1, E2, En, and the vector space X is all of Rn. So E1 is 1, 0, 0, etc. So I'll stop here and then resume with proving that every basis has, actually, yeah, at least I'll state it, that every basis has the same number of elements.